is not quite started yet, but we are close. Class will begin in 10 minutes. This. And let's just make sure I can write. Right. Where's my keys? They were. Okay. What? Where it is? Whoa, I'm so excited. I just can't help it. I need a soundtrack. Yes, yes, that's what I need. Soundtrack for life. Fun. Where's the... It appeared on my couch. It was right there. So somebody returned it. And I don't know who.
Not via transporter or something?
Came into my classroom and it was right there. Not today, like last, what was it? We had thing Tuesday.
Wow, that's impressive.
Yeah.
Hello.
What's this here for?
We are going to use it
Wow. That's wild.
to show a chemistry demo.
Cool.
Because it makes the chemicals light up from below.
Whoa.
Yeah.
That's insane.
Do you even know what one of these is?
Yeah. Is it one of the ones that makes it go on the screen there when you look at it?
Yeah.
Yeah. We use them in elementary school.
Oh, yeah. The classic Simpsons line. Where are we going to find a really old piece of technology? To the school!
Do you even know what one of these is?
I don't know if they use them in schools anymore. It's been a while.
Exactly.
Yeah.
So we use them.
But they're still using them. Yeah, my first year university chemistry professor who taught Ms. Handley, Dr. Dingle was literally his name. He had
We
one
had
of,
Mr. Donkers once. I hated that man.
they had like a scroll on either side. Have you seen those where you scroll through the notes?
No.
So instead of putting on sheets, you'd have a long ribbon, and you could just scroll from page to page much faster. He would scroll through the notes while talking, but he never stopped. So you'd look up to write down the notes, you'd look down, and you'd look up, and the notes would be in a different spot. And he stared into the light. So he'd look like this, and you'd always see the light coming out of his eyes, and in a complete monotone.
That's great.
It was horrific.
Sounds fantastic.
And then I had to stop telling that story for a while,
Wow.
because his son came here.
Oh. That's rough.
Dr. Dingle was a brilliant theoretical chemist.
Oh, that person was brilliant. His name was Mr. Donkers, and he was like the equivalent of what Mr. Rodriguez is, except he would come to what our equivalent of Omni was because we needed a counselor present.
But he's not a general counselor.
Yeah.
That's hilarious.
Yeah,
I think you mentioned that before.
Yeah, and then he'd basically sit there and be like, "Ah, yes, you gave me luck and
Right.
difficult." He was an awful person. He was the one who told me that I should go to auto body mechanics or whatever.
Actually, it's good advice. Make good money.
Yeah, but look at me. Do I look like the type of person who just really wants to touch a car?
Well, no, but if you did,
I was like, I want to go to medicine, and he was like, but have you considered auto body? And I was like,
consider auto body.
no, I haven't. Actually, you know why?
Maybe he had a quota. He has to get this many kids into auto body mechanics.
Yeah, instead of having like careers day, we had trades day, where they taught us how to like roof things.
No,
That didn't actively discourage us from going to college.
no, that's not good.
Yeah.
It's not good the other way around either, but that's not good. Like if it's good day
I
to
think
day.
you should just let people do what they need to do. Like they actively discouraged us from going to college. They were like, everyone should go to a trade, and we were like, why?
That's not good.
It's not what I want to do. That was the only day.
I mean, trades are lucrative, and I wish
I don't know what the link
the,
does.
the area where universities completely fail is that it would be amazing if they had more things like trades, in that you could be getting paid and doing the work as you're learning the material. It'd be fantastic.
I was not here on the day. Could I?
Did you have I haven't handed out the new notes yet. So.
Yeah, but my test.
Oh, yeah, you can come see me in tutorial or in between. We're gonna get started with class right away.
Okay.
Yeah, but it's in the box. I have it. You can come see it. Okay, notes out. We're gonna get started. Bell has gone. The glass is Riz. I wonder where the flowers is. Spring has sprung, the grass is Riz. I wonder where the flowers is.
Okay.
This spring hasn't sprung though. I don't know why I called mine. Okay,
Okay.
consider this first reaction. Which side has which? Considering both enthalpy and entropy, which side favors which side? Also, we have magic words.
Entropy is on the product side.
Entropy is on the product side. Product side? Entropy? Solids versus gases?
Oh, no, reactive.
Reactants. So, and what kind of entropy? High or low?
High.
High. So we've got high entropy here. So it's going that way. And which side has minimum enthalpy? What do we call that side? Not the right side.
Yeah. Or
Products.
It's been a long one.
We've-
I used to track people down this morning for their jobs.
Fair enough. So, so this side is favored by enthalpy, minimum enthalpy or maximum enthalpy?
That's maximum.
Minimum enthalpy.
Because it's the easiest to.
Because when we're looking for minimum enthalpy,
Yeah.
we're looking for the side that looks like that, the side that gives off heat, because it's missing all of that. So that is the side with minimum enthalpy. That is extremely messily written. I'll try and write it better here. That's an A in there for enthalpy. Yeah, the S. Woo! No, spontaneity is different. I like the idea that this S stands for, oops. Oh. S stands for chaos. And H stands for heat. Because it's chaotic. So we're going with the last letter.
What?
Stochastic means chaotic.
Which one?
Stochastic.
Oh, stochastic would work. Yeah. Stochastic, but how many of you have heard the word stochastic before? Yeah, that's not gonna work for class. Some people have heard of it. I think I've read that word like 7 times in my life.
Well, what does it mean?
Chaotic. Attendance, class dojo. Nope, this is the wrong attendance. You are not science and ethics. You are chemistry 12A. Attendance. Hey, there he is. Dylan? Yes?
Yes.
Dylan, do you want to preemptively move to like over there? Eric?
Wait,
Yeah.
I'll try here and I'll try this.
Echelon? And Felix? There we go. Inara? There. James?
Yeah.
And Chloe? And Luca? And Luce? And Martin? There were Martin, you were supposed to see me today. Milan? He's not here anymore. Yeah, he's still on this list. Nicholas? There. Sabine? There. Sonia? No.
I knew you were gonna say that.
I know, I gotta correct this. Sophia? Yes. Taylor? Yes. And Teddy? Yes. Oops. Inara, if you want to see your test at the end of this class really quickly. Oh, right, you have. I was thinking of which ones I had from last time. Okay, I think we've answered all of those. Which side is, so, what you get is when they oppose each other. Let's do that in the same color, so it's color coded. Wants to go to minimum enthalpy. The other side is favored by high entropy, so you have competing forces. And that's the case in which you have an equilibrium. So if we consider both enthalpy and entropy, those are the cases in which we're going to have reactions that are going to have that dynamic equilibrium. Same thing, do this one. Will this go entirely to products, stay at reactants, or go to equilibrium? Label what delta S and delta H are. That is. For the people who came in late and weren't ready and not writing things down? Those people? Those people who are late?
I wasn't late, I was 30 seconds late.
You just said you were late.
By 30 seconds.
Do you know how rare it is as a houseman? I get here on time and I'm ready to go. Gotta be here. Take advantage of those valuable moments. But Max and Min. Oh, ignore the diagram. That was just explaining something to someone. Yeah. To make a clean set of notes, we can get rid of that. And then scrolling. Now I'm going to ask. Oop, where's my map? Eshwan, where's the delta S? Which side does it favor? Reactant side. Why? Yeah.
Gas.
Right, because gas. Excellent. So delta S.
Also, does the heat there do anything for S?
No.
Okay.
The heat only does something for delta H. Reactants, max entropy. Eric, delta H.
It's on the reactant side.
And what is on the reactant side? What is on the reactant side?
There's heat.
Yep, but what would we phrase that as?
Minimum entropy.
Minimum entropy. Sabine, which way is it going to go then? Entirely products stay at reactants or go to heat. Stay at the reactants. And often we'll show it like that, an arrow going the other way. Because if we had carbon, it's going to go completely that way. Or sometimes you'll see it written like this. It will not go. Either is acceptable, you'll see both in textbooks. But what it means is all the energy term and the entropy term in the reactants, that is a reaction that just won't happen. You can't unburn something, because essentially this is trying to take some sort of gas that's been given off, add some heat, and turn it back into the solid form. That would be an incredibly difficult process. It's like unburning paper.
What do you mean incredibly difficult? Like, it's still possible? Or?
Well, you want to unburn paper, you have to grow a tree, and it captures the CO2. It can be done, but you divide it up into a lot more steps, and each step has to have a way that you can get there with a lot of energy.
There's no way to like all like the carbon in the air out there and from it to put it back in.
No, not really. I mean,
Is it a
3D.
system?
If you have a little tiny 3D printer, theoretically.
There's no like chemical process.
Well, yes. Get a tree, capture the CO2 molecules through photosynthesis, develop the fibers, repulp it back into paper. You've done it. It's just really difficult. It's not an easy one. Or if you had a way of putting each atom exactly where you wanted it to and got it, like that would be the ultimate catalyst. Would be like boom, 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 individual 3D printer. A going to 2B plus heat, delta S and delta H. We could probably do this one on the fly. First one, Teddy. Which side is favored by delta S?
Products.
Products. Oh, right. And you're supposed to tell me what it says.
Max entropy.
Entropy. James, delta H.
Products,
Good, we're getting used to the terminology. So both of them are going to products. Chloe,
Wait, why
which
is it
way will the
minimum
reaction
enthalpy?
go?
Yeah, why is it?
There we go.
Not maximum.
Pardon?
Why is it minimum enthalpy, not maximum?
Which side is favored for a potential energy diagram?
Potential energy?
Yeah, which side is the favored side?
Oh,
Right, the product
Right.
side. So on that side, because this is the heat side, this heat came out, right? And so this is minimum enthalpy.
oh, I see.
It is less than where it started from.
Okay, I see.
Yeah.
But it will always be maximum.
Always maximum entropy and always minimum enthalpy are favored. So if you ever have the same on both sides, like it's max entropy and max enthalpy, well then you know they're opposing each other.
But can there be a minimum entropy? Is that easy?
Sure, solids are minimum entropy compared to gases.
Oh, but if we're writing the most, it'll always be maximum.
If you're looking for the one that's favored, that's always the side with maximum.
Okay,
Because they're gonna be different on both sides.
okay.
Well, theoretically. There are a few cases in which they're the same. You have gases being split up so that there's two molecules on one side and two on the other. You'll have an even amount, and then we'll just go with entropy.
If the heat was on the other side, would it be max enthalpy?
Then if the heat was on the other side, so if you had a endothermic reaction, then the heat term would be on, so I'll do that in pink. I'll erase this afterwards. But then it would be like this. And then this would be reactants, would have minimum enthalpy, and then you go like that. Whereas right now, the old way, it's 2 to that side. Here, let me hit I have the undo button right here.
It's still products, right? Is that just an example?
Wait, so it'll still be minimum enthalpy?
You're always looking for minimum enthalpy.
What the heck? I don't get this.
It's okay. Read it.
Why would it be? Leave me alone.
Look this way. Which side has minimum enthalpy right now and why?
The right side of minimum enthalpy because
Don't
the
interrupt.
product side has minimum enthalpy because it's exothermic, so the
Yeah.
right side's gonna get warm.
Okay.
But if
And,
you put the heat to the left, won't it be endothermic?
yeah, and if, let's go with one of
Then it's
these.
gonna have maximum.
So we had this one, the heat was on this side, so the reactants had minimum enthalpy.
Oh.
So it just changes sides depending on where the heat term is.
Oh.
So this is endothermic. So that's a terrible diagram. So that side is minimum enthalpy, so reactants have minimum enthalpy. So we're just looking for the side, which side is delta H favor?
Okay, now I see.
And then separately, you consider delta S, which side is more random. In this case, it was reactants. In this case, the gas is on that side, so it's gonna be product.
And then the delta S is always going to be entropy.
The delta S is always entropy, delta H is always heat. Yep. And so for reaction to go 100% unaided in the direction of the arrow, what has to happen from left to right for delta H? What is delta H doing from left to right?
It's
More crazy.
Delta
it's
H
losing
is,
heat. It's losing
Oh,
heat.
yeah.
is it going up or is it going down?
Yeah.
It's going down. We're going this way. So for a reaction to go 100% unaided, delta H must decrease. And delta S must
Increase.
increase. You don't have to do it. I mean, you may have to light a match, but it will now go spontaneously on its own.
Could H also increase and S decrease, or would that not?
What that would do is now for a reaction to not go at all,
Oh.
then, because you put both forces against it. And so that would be a very difficult reaction to accomplish. I mean, we still try. You ask, like, can you do it? Well, if you could lower the delta H so it's not that much of an energy barrier, and then find a catalyst that gives you the perfect geometry, and then provide a lot of energy to get that reaction to work, well, you might be able to force it to go against both forces. I spent an entire summer doing that with a particular reaction that would have been absolutely fantastic if we could have gotten it to go. University of Victoria, the professor would hire a student every summer and just said, do this with this reaction. We go through test after test after test after test with different catalysts, different reactions, different everything to try and make that reaction go. And at the end, I was like, I think the 6th student to do that. Like, this is 6 years running. And mine was the last one, and I then finished off, and we conclusively proved that that reaction absolutely cannot go. And if I had made it go, I, along with the name of the other 5 students, and the professor would have had our names in a paper because we contributed. But nobody cares about proving that something doesn't work, so they don't write a paper about that.
Oh,
What was it?
but
It's
what
still
about,
like evidence.
Yeah, no, that's one of the problems in scientific publishing is that positive results are considered more valuable than negative results.
It wasn't published at all.
So it wouldn't publish. We tried all these things and it still didn't work. Nobody wants to publish that.
So now, no one's gonna know that they can.
No, unless they contact him. He is the expert in that particular type of chemistry.
What
Yeah,
was- what
and it
was-
might be a note in some letters to the editor that he would send in or something.
What was the reaction?
I don't even remember. It involved fluorine,
I love it.
and that's it.
See, this is why no one cares. You don't
Yeah,
know.
my brain's like, whew, no idea. Okay, now considering both forces, I would like you to label these. Which side has maximum entropy, which side has minimum enthalpy, and then put the arrows correct.
Gases are valued higher, right, than aqueous solutions?
Yeah.
Oh yeah, I was just thinking about that like 5 minutes ago.
Yes,
Yeah, I was. Yes, you know the problem is very fast. So which side are you going with then?
Just both gases, but it's which one has more molecules.
They do. Yeah, they do. And while the solid may not react because of low surface area, it's still going to react. The fact that the solid doesn't affect the equilibrium. For entropy, yes. Yeah, yeah, more random. Yeah, yeah. No, yeah, why is that out? Put away your laptop.
Mr. Nicole, for this one, it's, they wrote the all gases, so it's based off the number of molecules.
Number of molecules is an important thing to consider.
This one's just gas, the other one's solid as well. So it's-
Oh, I'm not gonna tell you. But, if you're looking at just solid and gas, I think you might wanna relook.
This is so look at this, and it does.
this one, because there's like 1, 2, 3, 4, 5, and then here there's also 2, 3, this is gonna be maxes.
I don't know how you count this.
Like the front and back, so there's like 1 here.
No, there's, you put 2 front things on something that only has 1 front thing.
Wait, oh wait, no,
You
no,
can't
no.
put anything in front of the oxygen.
This will be
CO2.
2. I mean, I gotta count them, these are all gases.
Right.
So 1, 2,
No.
1, 2, 3,
No.
4. 1,
Yes.
2,
Okay.
3, 4, 5.
Sure, but you want to count per side. not
Yeah,
just-
2 and 3.
Yeah.
So entropy is gonna be here, and that's gonna be maximum.
So I'm not going to confirm it.
Would this
I
be,
mean,
That's okay.
so would this be from this side?
If both things favor that side, then yes.
Why? They don't. Or they would track less.
They don't?
No, they can't, like, because the heat is on the product side.
Oh, then you would have arrows going. Okay.
I just ignored the salt side, but I see because that is the truth. If you don't understand the terms, it's not my fault.
Let's go with Sophia. Label either term. Which side is favored?
Sorry?
Which side is favored using either term?
Oh.
That cleverly confused me. Which side is minimum enthalpy and which side is maximum entropy? You can just name one of them.
Products have minimal enthalpy and reactants have maximum enthalpy.
And hold it. Products of minimum enthalpy and reactants you said have max entropy. And what does that mean for the arrow?
It's pointing in both directions.
It's pointing in both directions. Well done. Dylan.
For the next one,
Yeah.
the right side is gonna have maximum entropy
Why?
because there's like, both sides are gases, but there's more on the right.
Right. This side is how many?
That side is 3,
3,
and the other side is 2.
2. Excellent.
And then for enthalpy, because the kilojoules on the right side, it'll be exothermic, so there'll be minimum enthalpy on the right.
Yeah.
So the arrow will be pointing to the right as well.
Yeah. So now we have arrow pointing to the right. Last one. NA.
The reactant side is max entropy and the product side is minimum entropy, and it's pointing towards the reactant.
Why is the entropy, max entropy on the reactant side?
Gases on the reactant side.
There is a gas on the reactant side. Nope, that's good. There's also gas here.
Molecules? I'm not sure.
Why did you decide to pick that side?
Because there was more stuff with the gas.
More stuff with the gas. That's exactly right. The solids don't matter if there's gases, so you only consider the gases. And this side has 3, and this side has 2. And so you go with the more stuff. So that's good. So your maximum entropy is on that side. How did you pick minimum enthalpy? Shh, stop whispering to him. Because he can't hear you, I can tell. He's just trying to say words. And when he said the words before, he was good. Why did you pick this side for a minimum enthalpy?
It's up here,
So before, let's go back one. How did we pick that this side had minimum enthalpy?
There was heat.
There was heat. And this side, let's take one that was different. How do we pick which side on this one had minimum enthalpy? the heat, so it was the reactants. So if we go all the way down to here, which side has the heat?
Reactant.
The reactants. So we will take our minimum enthalpy, and that is also over here.
Wait, wouldn't it be maximum enthalpy?
No.
Wait.
Endothermic. Endothermic. Right?
Yeah.
So it starts here,
I see.
it goes up, comes down, goes like that.
My brain was still thinking like so.
Yep. And it went up by, it went up by how much, Dylan?
By plus 162.
162 kilojoules. Excellent. So, Nate, what kind of arrow do you get here?
The one that's going through the reactions.
One that's pointing through the reactions, yeah. So this reaction will not go.
Oh. Hebden. We
There's some
finished.
Hebden pages in there?
Yeah. Can we just do Hebden?
Nope.
Oh.
Because of the way the schedule has worked, with what classes are canceled and which ones do things, we are going to catch up first.
Yeah, extra classes.
Behind the other class?
It's not so much, well, yeah.
Oh.
I was gonna say, like, you're not, because it's not your fault, it's just that that's the way the schedule worked. But because of the way the schedule worked, yeah.
Are we starting a new unit or are we doing?
I always like that there's a cartoon I saw,
Mr. Neufeld,
but I'm gonna give you a demo first.
I was checking the hazard assignment for your unit,
Yeah?
and you don't have, for the hazard for this next unit, you don't have the PLOs written.
No, I used to not give them at all.
So we don't know
I
what
would
to
just-
do.
What?
We don't know when to stop.
Literally a decade of students before, but you just keep going until you don't understand. Every section, so like when I say, usually like, where do I stop? I just go like, well, here, we introduced equilibrium, so here it says in your book, intro to equilibrium. I also moved the up to here.
Also, these ones are different than what you assigned in the hazard.
No, those are just all of them.
Oh.
Yeah, just that's the
Do you want to
section.
do all of them?
It's up to you. There's minimum, and there are people who are like, I really get this really quickly. I don't need to do all of them. What I need to do is practice old exams. So they do the minimum and they practice a lot of old exams. If you don't understand the material, my recommendation is always do more Hebden. If you understand the material, but you're not getting the marks you want because you don't understand test questions, do more test questions. Where is the, oh right, it's over here. We have a new section of notes. It's so much fun.
Is it a new unit or is it more?
It is E. We also get to decide when our D quiz is.
Saturday.
No, what?
It's
Next week.
fresh, it's easy. We're starting a new unit, we'll forget.
So like literally instead.
Yeah, it's expensive, no?
Yeah, no, it is.
It's just on this. This is supposed to be.
When's our next quiz?
Maybe Saturday
What?
Or Monday, it's good on Monday.
or Monday.
Monday would be perfect.
Saturday's a short class, I don't know if you're looking at. Wow.
Well, are we ready for our
I
quiz?
only gave you two.
Oh, that's just so good. You started to do it. Yeah, just starting a new unit.
Dun, 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 dun.
Mr. Neufeld,
Dun, dun, dun. Yep,
we have a quiz on Saturday. What's going to be on the quiz?
D.
But that
But
was
like,
so easy.
what do we do? We just label the, you just give us equations and we label it?
Well, as always,
And like some multiple choice asking us what enthalpy and entropy is?
kind of. First, make sure you've done the questions in Hebden, so you understand the material. That can give you some idea of what kinds of questions there are as well. And then a reminder, you have access to,
Did you start live streaming?
oh yeah. You have access to, in terms of studying for the quiz, Nobody knows what they have access to.
We have access to the provincial.
Yeah, you have access to an entire test bank.
And you take.
So you should be able to do questions 7, 8, and 9 from 2000. Is there any D's on here? Nope, because they gave you lots of multiple choice. So we've got 7, 8, 9. So if I was to go back, oops, that's 7, 8, 9.
Yes. No.
Come on, load. So 7. Consider the following equilibrium. Equal moles of N2 and O2 are added under certain conditions to a closed container. This is similar to the reaction that you did the reaction mechanism to in the last quiz. Which of the following describes the changes in the reverse reaction which occurs as the system proceeds towards equilibrium? So it's moving equilibrium. You've added equal moles of N2 and O2. What's going to happen to the reverse reaction rate, and what's going to happen to the concentration of NO2? Consultation with people around you? No, don't tell me the answer. What's going to happen with the concentration of NO2? Don't look at the answers. With multiple choice, you're better off just answering the question, then looking for the answer. Don't look for the answer first. Bad strategy. Then you get fooled. What's going to happen to the reverse reaction rate? For that. Equal moles of N2 and O2 are added. So, what is the reverse reaction rate going to start as? No, again, I said don't yell at the answer. Tell me what reaction.
Answer.
Pardon?
Let's start as NO2.
It's gonna start with less product.
Less product. How much product is it starting with?
0.
0. So what's the reverse reaction rate with 0 product?
Increasing.
Increasing because it starts at 0. It's going to go up as it has. What?
The reactants already have.
Yeah. So if you start off with all of this, what's the forward rate going to be?
It's gonna be down.
No, it's going to be high, and then and then it's going to go down. So you answer. And then what's the reverse rate? It's going to start low and then go high, and then eventually they'll meet and become the same, and that's the entire unit basically. So what's going to happen to the concentration of NO2? What's going to slowly increase? What's going to happen to the reverse reaction rate is also going to increase. So whatever increase in increase is, A. Didn't you yell B?
Oh.
So did wait.
I didn't yell anything. That was Nick.
Why are they both increasing?
Anyway, again, how much product do you start off with?
With
0.
0. So what's the reverse reaction rate to begin with?
it's
Bigger than
increasing.
0.
What is it to begin with?
0.
0. It's not increasing yet. It has to get over, and then it will, yes. You're jumping just a step ahead. So it starts at 0, and then it's going to go up. What's the amount of NO2 that it's going to start off with? Right at time 0, it's going to be 0. And then as it makes more, then it will increase. So this is the questions, what is it going to be on? It's going to be questions like these. 8. A chemical equilibrium is described as dynamic because maximum randomness has been achieved, the pressure and temperature do not change, both reactants and products continue to form, the concentration of chemical species remain constant.
C.
What?
C.
D?
No, C.
C.
It's
C would be
always
correct.
going around.
Yeah. They continue to form. All of these are true, possibly about, except A. A is a little weird. But B and D are true. They're true about equilibrium, but they're not why it's called dynamic.
We
That's
haven't
a-
done dynamic equilibrium.
Yeah, we did. We went around a whole table, and I said this is why it's dynamic. It's because things are still being made and
Static equilibrium.
versus
Yeah.
the static equilibrium. Yeah. And then 9,
Dynamic.
which of the following results in an entropy increase, which is what we just were doing. We've got solid plus gas go to 2 gas. Gas plus 2 gas goes to 1 liquid. 2 gas plus gas goes to 2 gas. And aqueous and aqueous goes to a solid. Which one results in an entropy increase?
I think
gas plus 2 gas goes to 1 liquid.
No.
No.
I can't see it.
Oh, if you can't see it, yeah, you might be able to. A has 1 gas on this side and 2 gases on that side, so it's going to be A. Entropy increase. So if you want to practice, you have, don't reminder, you have all of those. Oh, go away.
They go to the water.
Yep. And now I am also going to get out I need to get out the next unit. So we are block A. There. So I'm going to use this particular reaction as a demo because we're going to talk about how reactions can shift. So you can have a dynamic equilibrium. You don't see any changes, but if you make a change to the environment, then you can see a particular change. And we are going to be up to, oh, come on. Page 6. Okay. Demo. And probably I need some blank wall or something to put this against. Let's do that. We're going to shut this off. And
Should we come up and look?
I'm going to invite you to come up and look in just a second. So far, it's just a light box. And let's go. Yeah. There, darkness. So I have.
Invite you up.
I will invite you up in a moment. Nothing's happened yet.
No, you just did. My bad.
No. There we go.
Don't look that. What type of light box is this?
Boom, boom, boom. That's about right. Yeah, that's about right. Okay. Oh, and cleverly I wanted to make it dark so you could see, but now you can't see the point of what I'm doing. So put that back on. Go back there. This is an equilibrium. This is, come back. Copper sulfate and copper bromide in solution. It is currently what color?
Blue.
It's all blue. It's all the same solution. So which side of the equilibrium is right now is it mostly on?
It's on the reactor.
Yeah, it's on the reaction side. Now, in an equilibrium, you can shift it around by adding things or changing the temperature. If I wanted to make it green, I would need to shift it to the right. So I need to increase this reaction rate, the forward reaction rate, to make it more green. I can increase it. Now, if I add more copper sulfate, that's just going to make it more blue. It will shift it, but then I'll probably get a very similar equilibrium. However, I can figure out bromide is colorless. So I have some NH4Br. And just as a reminder, if I drop that into water and it's soluble, what does it do? What are the ions in NH4Br?
Positive.
There's a positive. Which one is positive? NH4. So we got NH4 plus, which is an acid. Is there any H plus in our reaction? No. So as an acid, it's not going to affect this at all. So this is going to be useless. It's not going to do anything. But I'm also going to give off Br minus. So the amount of Br minus, let's choose a different color other than blue and green. The amount of Br minus is going to skyrocket. This is going to go way up. That is going to increase the forward rate. And what will that decrease the amount of if we increase the forward rate? Copper sulfate. So it should become less blue. It should become more green. NH4Br. Where's my little glass sticks? There they are.
Should we come out now?
Nope. You just stay where you are.
Damn. The whole thing.
I probably should have been on this side. I'm trying to display the colors on there, but also it allows you to see them over there. And it takes a while for it all to dissolve. This is a stir stick. Oh, yeah, then I'd have to get out a whole thing and then put it on it and then take too long. Okay, now you may come up. File by and behold the equilibrium having shifted. Behold, it is now green. Wow. Wow. Behold, turquoise is green. Turquoise isn't a real color. It's a fake color, like teal.
Do you get to just like decide what is and is not a real color?
Yeah, the
What other
real
colors
colors.
are
The real colors are the ones that are on the rainbow. Red, orange, yellow,
Orange is non
green, blue, indigo, violet.
So indigo
So
is
you're
a real
saying teal
color,
is a
but
real
teal
color,
isn't.
but
Indigo.
No, teal is not.
But indigo is.
Indigo is just a weird
What
form.
about in the spaces between the rainbows?
Hold, what is teal anyway?
Teal is like,
It's like dark turquoise.
yeah.
No, teal. Oh right, no.
Teal is
Teal is the color of Allard House, right?
Technically, yes, but it's more just like a bright blue.
Yeah, it's blue. That's why Allard secretly belongs to Privet. Yeah, because Privet owns all of blue. I don't care what colors you call them. They're all blue.
I'd say this
Yeah. Okay, has everybody beheld it? As soon as you beheld it, you may go sit down. I'll do another magic trick. People who haven't beheld it, because other people are standing in your way, come up and behold the change in equilibrium.
Goose is just taking it all in.
Yeah. Felix was like, right here, right away. I want to see.
Like this blue is out.
No, see, but that's our t-shirts are even that color.
No, our t-shirts have that color. Use like some darker,
Like
like
that's like a mix
indigo.
between-
No, but like our inner house t-shirts are light blue. That's just light blue.
See, like the green is green now.
Yeah.
It wasn't green before.
Okay. I'll send them a quick email.
What type of green would you say that is?
That's just like regular green. All greens are regular green.
Actually, even I can see lots of different shades of greens because we can. No, it's like an evolutionary thing. To be able to distinguish greens very differently, which is why when people try to paint greens, they often have a hard time painting greens because it just
You can just go. I'm emailing you.
because our eye can tell greens so specifically.
Okay.
It's not bad.
Now, the other thing I'm going to do is I'm going to do the exact same thing again so that we have a comparison. I should have just done this to begin with. Again, it's green. There's no such thing as turquoise. It's a fake color. Oh, like taupe. That's also a fake color. Taupe is like my mortal enemy of colors.
Yeah.
Like that's very
He's just doing it again. Wait, what's toad? What color
Taupe.
is toad? Taupe?
Exactly. You don't even know what it is because it's a fake color.
You have to put turquoise. Now it's going green.
And taupe isn't even, like it's not even a color. That's just what you call things that are like lightly dirty. If a wall has a lot of dust on it, it's taupe. Okay,
How's everyone dark green?
I think there's actually a little less of the, I think I put a little less of the copper sulfate solution in there, so there's a little less, so that affected the equilibrium. There's different concentrations. Now they are in an equilibrium, so it's moving back and forth. It's a dynamic equilibrium, but once the color's unchanging, we know that the concentration is the same, so nothing changing. How, if we're at this side, what could we add to make it go that way?
More sulfate.
More what? More sulfate. And we already know ammonium doesn't do anything, so if we add ammonium sulfate, we'll increase the amount of sulfate hugely, and maybe we can get it back to blue. So should I do the darker green one or the lighter green one?
Darker green.
Darker green? Where's there's the last of the stuff. No, just people came up with a lot of words for things that are just like the same. Hold on, what did we say? Darker or lighter?
Darker.
So that would be this one. Yeah.
Okay.
Just add it all.
White. Whoa. Turquoise.
Ah?
I like that color.
Now it's just a spell is very bright.
It's really.
Why is it just like white now?
I like
Well,
that color.
what I may have done is I've created a saturated solution of the ammonium sulfate. So it may be that I never get it to display it there because it's not going to be clear. But we can still see the change in color. What color has it gone?
White.
No, not at the very bottom up here.
White.
White.
No!
Green.
Come up and look.
White.
It's not white.
Oh, you can see it's white. It's different from the white.
Oh, yeah, the
Yeah.
side
No,
you
it's
can't
baby
see it.
It's
Yeah.
a different blue.
It's a different blue. It's blue.
Baby blue.
Yeah.
Baby blue.
It's baby blue. It went back to
So
blue.
baby blue's a
Yeah, no, if you haven't, come up, come up. You must see the equilibrium.
I-
No,
I
come.
really-
You're at the
I-
very back. I know you have to come up. Eshwan, Taylor,
I've
Nara.
seen it. I can see it.
Come up and look.
I said 20.
Behold the glory.
Oh, I've seen it though.
Like,
Oh my god, it's blue.
It's all like glowing. It's like you
Yeah.
discovered like uranium.
Oh, yeah.
Like a taste.
You can actually get uranium dishes.
Can you eat uranium? I'm
Well,
asking for a friend.
no. It's a poison. It'll give you heavy metal poison. Even if it wasn't radioactive.
What if I made uranium brownies? Those have really good brownies.
Yeah, they would kill you. Yep.
That's so delicious. I love over uranium.
There are people who collect uranium glassware. It was really popular in the 50s. It's just glass, crystal glass that's been made with uranium. And if you shine like a UV light on it, it glows. They're also slightly radioactive, so you have to keep them in a special container. Okay, so not only did you see the equilibrium go one way, we saw it come back the other way as soon as we added more stuff. We can change the equilibrium around by affecting the rate. So we increase the sulfate, we increase the reverse rate. That rate went up, and then the other rate had to speed up to accommodate it, but now it's shifted. So we also know that the concentrations don't have to be the same on both sides, because we're changing those around just by adding different stuff. This one's not as pretty. You had to come up to see it was blue, because apparently I don't know how to make an unsaturated solution. But I will now move it around. Bye. And there.
We have nap time now.
No.
It's nice and dark though in the stream.
Oh, sorry. Let me fix that. Boom. Boom. Ooh.
I'm still not
Are you counting down the minutes, Dylan?
Definitely not.
To the end of my class, which is so interesting. I'm hurt. Hurt, I tell you.
5-minute increments.
Okay, shift.
It's 5 minutes.
Oh.
It makes it
Yeah, we have 35 minutes left.
Oh no, I'm going to do this in a clever way.
No.
Equilibrium. There. A system's shift is. Okay, I better get rid of this.
That would have been really unfortunate.
Yeah, that would have been bad. This needle folds over backwards in an array of glass and copper sulfate and copper chrome.
That would not be good.
Dylan, you're finding that way too funny. I'm getting suspicious. Because you were up here longer than the other people. Did you move the cart in that direction?
No.
Okay. So a shift is, in terms of reaction, literally when we say that it's moving in one particular direction or it's moving in the other particular direction and which way it's going and by how much. And this is a negative feedback system. It is naturally built into equilibriums that have a reaction, because if we look at what we did is we increased the amount of bromide. When it shifts to the right, what happens to that amount of bromide? It decreases. When we increase the amount of sulfate, it shifted to the reactants, and then it decreased the amount of sulfite. This is a really useful property of equilibrium. It's one of the things that allows life on planet Earth, because if reactions just naturally inherently have this property, that means they tend to keep them towards the middle, and then you can use that to regulate your environment. A lot of things in terms of temperature use this. A lot of things in terms of reactions within your body, they use equilibrium to keep the concentrations the same. One of the areas we're worried about with climate change is that an equilibrium can be overwhelmed, and then it all just ends up at one side. This is all to do with Le Chatelier's principle. Le Chatelier's principle we're going to apply to temperature changes, concentration changes, and volume changes of gaseous systems. If we are looking at a system and it needs to be at equilibrium, what kind of system does it have to be? Sorry? It's a dynamic equilibrium.
It has to be
There's only,
you can go at both sides.
pardon? Closed. The best way to demonstrate an open system is if you're burning a fire, or you have any sort of combustion, the gas is constantly escaping. So even if there was a chance of it reaching equilibrium, that's not going to happen because you're always letting the gases escape. Now, that one has both systems on one side. That's written weird. Why did it? Is yours down on two lines like that? Here?
No.
No?
No.
That's weird. This should tell you principle, if a closed system in equilibrium is subject to a change, processes will occur that tend to counteract. What I find useful as a mnemonic,
Let's say counteract.
counteract.
Okay.
Whatever we do, mnemonic. Mnemonic. Whatever we do, nature tries to undo. This has worked really well in a lot of different areas. There's a lot of solubility chemistry that goes into maintaining lakes and oceans at a standard pH. There's a lot of calcium carbonate deposits in planet Earth. And if the lake becomes more acidic, it reacts with the calcium carbonate, it neutralizes it. If it becomes too basic, it will form more, it'll precipitate out. And that particular equilibrium will go back and forth and try and undo. So small changes to the environment lead to a relatively stable equilibrium within the water environment for the fishies. If, however, we are constantly adding acid to our atmosphere, that's raining in the lakes, eventually the calcium carbonate gets all used up. It's not an open system. It's not a closed system. It's now really an open system where we're just shoving acid in there over and over and over again. The equilibrium gets overwhelmed. I like that example because that is one of the few areas where we've actually done a good job. We've markedly decreased the amount of acid rains that exists in large areas of the planet. We've also healed the ozone layer. The ozone layer should be shutting down. So it's nice to have a bit of good news about the environment once in a while.
That means that he's closing.
Oh. Oh, I think
Yeah.
that, like shutting down, like going forward.
No, like the ozone layer was growing rapidly because I don't know if you've seen pictures of people from the 80s, but they always had like hair. And everybody absolutely loved their volume hairsprays. Used a lot of it, and it was filled up with CFCs, carbon fluorocarbons. Those act as a catalyst to break down ozone in the atmosphere, so our ozone just disappeared. And it was thinnest at the poles, so it was noticed first in the poles. And then UV rays and intense sort of radiation from space was getting far, far worse.
So that's because all the people using hairspray.
Basically, yeah.
Pesticides that
Yeah.
are being sprayed into the atmosphere.
Not as much the bug sprays. A lot of it was just hairspray. Because millions of people on the planet just spraying this stuff in the atmosphere eventually goes up, breaks it down.
People would go through like cans of
Yeah, cans and cans and cans. And we thought it was an inert gas. This is also one of the arguments for pure research. Scientists were just studying the atmosphere and had put up some detectors for things like ozone, just to measure stuff and do some experiments, and then realized it was getting thinner, and then figured out what was going wrong. It was pure luck that we had actually managed to figure it out before it got like really bad. And then we banned CFCs, like the entire globe. We still monitor, like a factory started producing in China, and it was like you could tell from the smoke plumes and how it was reacting with the atmosphere. That's releasing CFCs. The international body said, China, you got a factory there, and China's like, don't worry, we'll take care of it, and made sure it wasn't doing it because it affects the whole planet.
People were killed.
I don't think they were killed. They just shut down the factory.
They're just central work camp.
Just because somewhere's far away doesn't mean that they're going to do all of that. How many of you have traveled to China? And is it relatively normal there?
Can't see
Yeah.
the sky.
Pardon?
Couldn't see the sky.
What?
Couldn't see the sky.
You couldn't see the sky? Why?
I don't know. Beijing, the sky was.
Oh, the
pretty-
smog? Yeah.
Remember like on the news?
Yeah. You remember that equilibrium I showed you with the brown gas? When it gets hot there, that's exactly what that is. I know they've been looking at, they've been very concerned about the smog in the cities because that has grown so much. They're putting in more environmental control. Okay, moving on. Enough about the environment. We don't care. Any addition, which is a stress, or a change to the environment or to the system. And I'm going to add or subtraction. Because I added concentrations of things, but I could have put something in that precipitated one of them, and that would have taken it away, and you could do that. Works to the system works or shifts. Subtract. I swear I wrote the T. To offset. Subtraction. Is that, hold it, that might actually be a word. Where's my phone?
The fucking thing where you make it beef. The thing where it sings the song.
Well,
Oh.
it's black on a black thing. I can't ever find it.
Change the color of your phone case then.
Hey Siri, define subtraction. Oh, it says subtraction.
I don't think it's a word.
So that means it's my word. I invented it.
Why would subtraction be a word? What would it mean? Yeah.
Well, we've got sub, which means less, and
This fraction.
raction, which means to be putting up racks. So now that means taking down racks. Subtraction.
Yeah,
Yeah.
but rack is not spelled like that.
It could mean to do math badly. To do math badly. Does yours look like this as well? With this little piece here?
Yeah.
Sorry. I'm going to move it down a little bit. Yeah.
It is ours is fine.
If you could fix yours, that would be great.
Yeah, ours is already like that.
Yeah. I'm just going to go like... Okay, fill in all those words.
Ours is already like
heat.
good.
We have heat, and we're going to change the temperature. What are we going to do with the temperature?
Increase it.
We're going to increase the temperature. This is going to go up. If it's going to go up, which reaction rate is going... Now, this is where temperature gets a little weird. If you increase the temperature, what reaction rate increases? Forward or reverse? Both. They both increase. But it does affect one side more, because heat is on this side. So if we treat it like one of the products or react, in this case a product, we increase the amount of product, which rate increases the most? Products. No, that's not a rate. Forward rate or reverse rate?
Forward.
This rate?
No, reverse.
Reverse. So that rate would increase the most. They're both going to increase, but that's going to increase the most. And one of the ways to think about this, if that's a look, I'm going to follow with this, is that if this is an exothermic reaction, and I'll exaggerate it, and you're here, you need energy to get over this hill. If you're here, you just need a little bit of energy. So providing this person with energy will help them, but not as much. This is a billionaire. You give him $1,000, sure, help him a little bit. This person is living paycheck to paycheck. You give him $1,000, you help them out immeasurably. This is affected a lot more, even though you're giving both the same amount. Okay? So this person needs it more. That's my analogy. So if we increase the temperature, this is the same as adding product. Because this is an exothermic reaction. So this is only working for exo. If this was an endothermic reaction, then it would be like adding reactant. It's like adding product, and the product on this side is the heat term. Oh, I think I got carried away. Oh, yeah, no, I'm on track. Sometimes I just start writing things, and I go, what did I mean to write? So that would be the same as if we added AB. If we added AB, just like the equilibrium before, it would shift back. If we add heat and it's on the product side, it will shift back. So our stress is on the product side. I'm just going with it. Prod cut.
Can you?
Nope.
The computer has
Nope.
to say about that?
That's a subtraction.
Can you see what the computer has to
Yeah,
say?
let's see what the computer says.
Computer just has a little message that says
Prod.
Prodco. I like. That could be a good chemical
I
product.
just forgot about the T.
Yeah.
They just gave up.
So which way is the equilibrium going to shift? Left. I like the way the long, drawn-out nature. So towards reactants, it shifts left.
One of these things you're gonna be writing and you're gonna secretly be having a stroke and no one will know.
Or I'm having strokes all the time, and nobody already knows.
Yeah, that's.
And they call it Prodco.
I'll just die doing what I love, teaching my students. Twitching slightly as I stroke out. What are the signs of a stroke?
Oh,
Last one, last time your body
your
goes
speech.
You
You can't lift your arms
You
over
can't
your
smell.
head. Your speech is slurred.
Smelling
And
toast.
yeah, those are the three main
You guys are amazingly well trained. Well done. The one thing I used to check for, how many of you have heard that if you're having a stroke you smell burnt toast?
This was.
Yeah, that is a myth. That doesn't happen. It's because somebody who described having a stroke once said they smelled burnt toast, and some newspaper grabbed that, made it into a list of things that happened, and then published it everywhere in the 80s. So it's still going on, like the myth that carrots help your sight.
Something, yeah. Did you go?
I don't know if
No, don't they hurt your nails and your hair though? 'Cause
Have you heard that if you eat lots of carrots you can see better in the dark?
Yeah.
Yeah.
World War II propaganda.
Yeah, but carrots
Are you
help your
sure?
skin.
yeah.
What?
They help your
Carrot
skin.
gin.
It helps like your coloring. It's like weird.
Oh, if you eat, they have beta carotene. If you
Wait, why don't they help your eyes?
Technically there's a vitamin that in them, if you don't have enough, your eyesight will go bad. But in World War II, they invented radar. And they didn't want the Allies did. They didn't want the Axis to know, Germany, when they're flying over and doing the Battle of Britain, to know how did they get their planes up there so fast. They knew they were coming, and they didn't want to let out that they had radar. So they put propaganda out in the UK saying, our pilots are up so fast because we're feeding them tons of carrots, and they can see the planes coming further. And then they fed them lots of carrots, like they actually did it. And then those pilots all went home and told their families, carrots help you see in the dark, because they also believed it.
Oh, they actually just have like really nice hair.
Yeah, it was all just.
Did their skin turn orange?
No, you have to eat a ton of carrots for your skin to turn orange. Although I do remember when I volunteered for the hospital emergency room, this like person just like bursts in, like both doors just slam open, and he is like screaming. He's so scared, and he's like kind of orangey purple. And what he had done is he'd gone on a mega dose of vitamin regime, not realizing. So he had both very orange skin from the amount of beta carotene he'd been taking. And on that particular day, he took too much niacin. If you've ever taken niacin, you can get hot and prickly. It's just a side effect of taking a lot of it. Yeah. So he thought he was dying. And the nurses just looked around and they just almost collapsed laughing because apparently they've seen this a lot before. And they're like, he's fine. Just stop taking all those stupid vitamins. It's making expensive pee. Okay. I would like you, if this is time T1 right there, and this is the concentration of those, I would like you to draw which way you think those concentrations are going to go and what the curve is going to look like. Okay? We've already said which way it's going to shift. Draw it. Draw it. Draw.
Tell me what to draw.
What? So these are the concentrations A, B, and AB. So after we add the heat, it's what's it going to look like? Yeah. Are they going to go up? Are they going to go down? Is it going to be a curve? What's it going to look like?
All you gotta do is make
Because they'll go, and well, when will they go up the fastest? So what will your curve look like? This is like almost calculus. Like, what does the curve look like? Or pre-calculus?
So would it be the other way around?
You're drawing. Drawing.
Okay,
I won't hit Sophia in the head.
I know.
Nothing to do.
I know what's gonna happen.
Maybe like this?
Oh wait, it's.
Draw a straight line at first, and then at T1 is when the curve happens, and then show what happens.
Oh wait, I know this.
It's gonna make a T1.
What's your new phone?
You're doing a potential energy. Don't do a potential energy diagram.
Curve.
If your diagram looks anything like this, you've just confused diagram. Don't do that. As a oops. As a hint,
Oh, I know.
as a hint, what should the lines look like after equilibrium is established?
They all meet and they like level up.
And then they level out. So they're going to go in a direction, and then they're going to level out.
Oh, I know what's gonna happen.
Dylan now knows what's going to happen.
Would A and B go together and then AB would kind of.
Watch this be completely.
Yeah, so
A and B are gonna go up and then AB is gonna go down.
Maybe it goes up.
I think I just made some red.
so wait, so you're saying down?
Wait, Mr. Newfound, I think I have it.
Yeah?
It goes down. A and B are gonna go down to meet
Like
A,
this.
B, and it's just all gonna
Would it be like,
flatten out.
I don't know if you.
And then they're going to flatten out?
No. Bring them all the way down, like
All the way down?
just to AB,
Here?
Yeah, and then once they get there, flatten them out. Yeah.
AB goes up. because-
Okay, just to go back to here.
And B and
Then
A go up.
AB's
Which way is it shifting?
To the left.
To the left. So which ones should go up?
A and B.
A and B. Which ones should go down?
AB.
A, B.
That's what I said, Mr. Newfound.
I know, you're right, but I have to make sure that everybody's on board.
Okay.
I don't worry about the people who are right. I worry about the people who are wrong.
Dylan is wrong.
Well,
Okay, we don't need, this is a safe place.
It's not
People are
that.
allowed to be wrong.
It's not supposed to be a straight line.
And it's also not supposed to be a straight line. Felix, how, when it starts, when will it change the fastest?
Right?
I was really wrong.
Or no. Yeah.
Right at the beginning.
No,
Right.
sorta.
Because if I've done the change,
The highest tangent line.
highest tangent line, yeah. Because if this is going to decrease, it's going to be fastest right at the beginning of the change. And it's going to decrease. But if it's decreasing, that means it's throwing more onto the other side. What is that other side then going to do with it?
Increase.
Throw it back. And so this change starts off sharp, but then levels out
Oh.
and slows down.
Yeah, I was
Wait.
way.
I thought it went up.
Yeah.
Why though?
Why does A go up?
Because it's going to the left
Right.
for reaction.
So then, that's the type of curve. But it should look,
Oh, why didn't you just do that?
no reason.
Good job, that looks great.
Yeah, yeah,
Doing fantastic.
go away.
Oh my god.
And what does B do?
The same.
Yeah. Does it go up the same amount, double the amount, half the amount? Same. So this should be the same. So these amounts,
What the heck, now it's a
and what does the AB do? Goes down. No, it's A plus B, so this is balanced. So all of these distances should be the same. If I was to go along with all of these, this would be length, let's say L. This would be length L. This would be length L. And the amount they shift would be reflected by their stoichiometry. So they're balancing. They're in a 1-to-1 ratio, so the amount they shift is all the same. Where they are doesn't matter, because you can have an equilibrium at any concentration. But when they shift, they're shifting according to the reaction. So it'd be a 1-to-1 ratio. So the reverse reaction rate did what?
Reverse reaction rate decrease. No, it's increase.
It increases. Now, we increased the temperature, so what happened to both rates?
They both increased.
They both increased, and they both increased right away. We're assuming we changed the temperature right away. So the reverse reaction rate spikes, and the forward reaction rate spikes, but they spike in different amounts. This one spikes most. And then what would happen to the rate over time? What is this concentration is telling to the rate over time? It's going to spike and then decrease. Spikes most, then decreases. This one spikes, but it's less than the other one. So what's going to have to happen to it? Well, if the other one, I got a little spot here for a graph. So this is for rate over time. And let's use cool colors. So we'll make forward that one, and we'll make happy faces reverse. Good? Actually, that might be hard to
Can
read.
you throw the happy faces around?
I'm going to go, that one is the reverse rate. Good? Okay. So at the beginning, what is the rates?
It's
Equal, different,
equal.
they're equal. So the beginning, the rate is like this, and they're both the same. They're overlapping. We increase the temperature. Which one spikes the most? Reverse spikes the most, and reverse is our little flowers. So reverse spikes the most, rainbow spikes the
It
least.
doesn't spike like that though.
When you change, when all of these, we assume the change happens right away. So we just increase, it was at 25 degrees, now it's 100. So the rates just spike. And I am also going to make this a little bit bigger so that I can show the difference more. So it spikes, that one comes down. Now what's going to happen to this rate? It's going so much faster, throwing stuff to the other side.
Then decrease.
And then it decreases. What's going to happen to this rate? It's going to start to increase. And eventually they will be the same. So you'll get this rate coming down and then slowing as it shoves more to the other side. And this one will increase as it shoves to the other side. So this is the rate graph. Same forward plus reverse. Same forward plus reverse. But in here is where we have the change. Reverse spikes more because of increase in temperature. It's the side of the heat term, it gets more of an advantage. And then it comes to a new, so this is not at equilibrium. Equilibrium, equilibrium, not at equilibrium. And you get that rapid change, whatever it is. So now we have three types of graphs. You have a potential energy graph. You have graphing the concentration that happens. And you have a rate graph. Excellent. Woo-hoo. Oh, so, hands up for quiz on Saturday.
Monday.
Hands up for quiz on Monday.
Saturday.
Monday.
Monday carry.
Go back to Saturday.
Monday.
Hands up for quiz on Saturday.
No.
Hands up for quiz on Monday. Monday clearly carries.
Yeah. This new focus, I see my test.
Yes. Did you see the online?
Yeah, I saw the online.
Okay. Also,
Like I genuinely
what folder did this class get? Red or blue?
Red.
You need a red folder. Eventually. But if you just want to quickly look at it. Who should I give you? I have. You know, Rory Henderson. What sport do you play? Yeah.
Who's he at?
Rory Henderson. Oh, that is ancient. I only recently rediscovered that one.
Mr. Newell, come here.
Yep.
What number is in that?
5.
Oh, he's so colorblind.
It's not a matter of colorblindness.
Try with light
It-
color.
I've diagnosed 3 Science 10 students with color blindness in class. We're good for today. Yep, this afternoon.
Thank you.
Thank you.
Wait, this
Thanks
isn't
for
my
streaming,
test.
pal.
Who did I give you?
Nara.
Oh, sorry. Sorry, Nara.
This takes one of like-
It was right on top. It moves things around.
I was like,
I put yours aside and then grabbed yours when I
I was
put
looking at it, I'm like,
Wait a minute. This isn't my writing. Yep.
what's the T?
This is red.
Big, big.
Thank you. It's red.
Is this part the same thing?
Probably, yeah. Then communicating is the written part.
Okay.
But I should be.
Multiple choices, like, we get
Do what?
Isn't
But we had already started.
No, I know, but I'm telling
You won't know. Only on the.
Because it's 5. Okay.
Hey, and I was 30 seconds.
It's copper chloride. I was it this? No, it was the science 10s I mentioned it because they did a reaction with one of those things. That is, you're welcome. That's how a girl tried to kill her friends in Alberta.
What the hell?
She added that blue solution, or the copper sulfate, which becomes blue, to a blue slushy.
But like the powder, right?
Yeah,
It's just
yeah.
like-
That makes sense.
But she
Yeah.
added this.
Yeah, she essentially added that to a blue slushy, mixed it up, and gave it to her best friend.
Did the friends
Now her best friend then luckily shared it with all of the friends, and so she didn't die. But they had all dropped to the ground like foaming at the mouth because they had heavy metal poisoning. And if she had drank all of the original, she would have died. But as it was, they all got to the hospital. They had to do chelation. They had to pull the heavy metal out of their body. There's some emergency room stuff they could do, and they all ended up being fine.
How did they do that? Like a magnet?
No. Chelation is a chemical compound that you eat, and it binds metals really well. It'll also suck other metals out of your body that are good for you. So you need to also then up your minerals and vitamins after you have that kind of treatment. But it got all the copper out. And you could process
What
it
happened
into
to the
the
girl
copper.
that tried to kill
Now,
her?
in the girl's defense, her best friend went out with her ex-boyfriend without asking permission first.
Oh.
So, like, clearly poisoning.
And then
yeah.
she tried to murder her.
Yeah, so she had to murder her.
Obviously,
How about this one?
That's tea, that's tea.
Thank you for the
That-
story time.
Right?
Okay, that's nothing.
That's a lot of tea.
That's nothing.
That's a lot of tea.
That's nothing.
The girl tried to murder
What?
her friend.
Sabine, what color is it? Or color?
There's no 7. There's no 7.
Okay.
Hold it. Are you serious?
No.
Okay. I've been looking at colorblind tests all my life and I've never not seen the numbers. Except there are ones that only colorblind people can see. Because they make all the colors so that you can see color vision, it disrupts the number. But if you're colorblind, it takes away some and then you can see the number.
I'm assuming that's what that was.
Yeah, that could have been what that was.
I tried so hard to see something.
Yeah, we were like, okay.
What's going on?
Like, there's something in this. Hey, wouldn't it be funny if we... Bye.
See?